Okay. Thanks, Manuel. So last time we got as far as talking about Gaussian processes, and I just introduced you to this fact that the world can become inconveniently non-Gaussian. In those cases, we have to approximate, and I mentioned that a classical approximation is made by making a second-order Taylor approximation at the log mode, actually, I should say here, the logarithm of the mode in here, and replacing that with the Gaussian. And that was an idea that was developed, I guess, in the 18th century by Laplace. Not in the context of Gaussian processes, actually in the context of beta binomial distributions. Which is, I always think that's quite amazing. So he invented the Gaussian distribution to do Bayesian inference. Okay, so I mentioned the covariance function. If you were sort of, in the last lecture, you should have got the sense that the covariance function is very important. Because basically it's the only thing you combine with data in order to get your predictions. So all your modeling is going into two things. One, you're sort of saying that your data points are jointly Gaussian. So that's a strong assumption, although not as strong as some people think it is. But it is quite a strong assumption. You're deciding that all your data points are jointly Gaussian together. So, for example, outliers don't conform to that. Then you're also making some assumptions about the length scale or the overall scale of the process. So those parameters are embedded in this matrix K. So they're inside this covariance function here. And the question is, well, how do we find those parameters? So if you use the normal kernel methods, they sort of would tend to cross-validate. But in Gaussian processes, we do something slightly different. So there's two parts to this expression here. One is this determinant of K, and one is this e to the power of this quadratic form. So you should notice immediately that the data only appears in this part, where K appears here. So in some sense, that must be a data-dependent term. Now that's unusual because it looks more like when Arthur was talking about kernel methods, that looks quite a lot like the regularization term, because that was of the form F transpose K inverse. Well, F transpose, it's of the norm of F in the kernel Hilbert space, which would be given here by F transpose K inverse F. But this is the data term, so that's something to be aware of. And this turns out to be some form of regularization. So what we do to find these parameters is we just do what we normally do. Well, the simplest thing you can do is you maximize the likelihood of the system. So this is a probability distribution, so you can do maximum likelihood in the system. And if we take the log likelihood, which we typically do for convenience, the maximum of the log will coincide with the maximum of the likelihood. Then we see that these two terms separate out into something which is, this is a quadratic form and this is a log determinant. So what I want to do is just investigate what those little terms do. I mean, they don't actively do this. This is just a function. I'm just trying to give you the intuitions of, like, you know, these terms aren't conscious, not like deep neural networks. They're just bits of maths. But I want to try and give you an intuition for what goes on in these terms. So if we think of it as an error function, so we're trying to minimize an error function. Habitually in optimization theory, we minimize. That means they're pessimists, right? They want to minimize costs. So since they do that, they decided that long ago, then it's often useful when you're talking about optimization, to talk about minimization. So the error function would be the negative log likelihood, removing this constant term here. And then you can clearly see we've got these two terms. So before we go into those two terms, I want to give you some intuitions about how I'd like you to think of these covariance matrices. Or one way of thinking of covariance matrices. So a very useful decomposition for understanding the objective function is to think of the sort of eigenvalue decomposition of the covariance matrix. So since this is a symmetric matrix, its eigenvectors are orthonormal. It's an orthogonal matrix. So those eigenvectors represent a sort of basis that gives this a rotation. And the eigenvalues, lambda, represent a scaling. So what I've shown you here is an ellipse of the two-dimensional Gaussian process. It's got two eigenvalues and two eigenvectors. The eigenvectors are giving me a rotation, and the eigenvalues are giving me the scale. So they represent the principal axes of that ellipse, the one standard deviation ellipse, right? So that's lambda squared here, so that's sort of like the variance. The eigenvalue squared is like the variance, and lambda is a bit like the standard deviation. So they're telling you how the Gaussian orientates. So if you know about principal component analysis, you'll know that this is typically what you look at. You compute your empirical covariance of the data, and then you compute these principal axes. But you can also think of it as a way of sort of describing the Gaussian itself. Of course, it's actually quite difficult to analytically compute what these eigenvalues and eigenvectors are given your covariance function. That's the sort of thing that Arthur was, I think, talking about, certainly in his first lecture. You'd love to be able to do it, but analytically it's very difficult. That would be eigenfunctions instead of eigenvalues. So we're just thinking of the matrix for a moment. So let's look at this log determinant term. So this log determinant term deals with capacity control of the model. It's actually the sort of regularizer. And the reason it does that is because if you look at just these eigenvalues here, so I've taken the diagonal vector of the eigenvalues from that thing. They actually describe a sort of little basis. So that first point there is lambda 1, 0, and the second point is lambda 2, 0. So they're just giving us an axis like that. Now the determinant of lambda is just the product of its diagonals. So that means that the determinant is basically the area of that square. Nice and simple. Of course, these could be negative, in which case it would be a negative area or something. But we'll deal with that in a second. Now the interesting thing is, okay, so if we add an extra dimension, then of course we get a volume. So this thing here, the product of its diagonal, which is its determinant, represents the volume of the eigenvalues here. And of course, if we rotate, so if we apply those eigenvectors to this doesn't change, and determinants don't change under rotation. So the determinant of R lambda is also given by the product of the eigenvalues, right? So actually what this term is saying, the determinant of R lambda, it's not quite the determinant of the object we're interested in, which is this thing, but the determinant of R lambda is giving us the volume on which these two standard deviations sit. Now, of course, that's not quite the thing we're interested in, but as I said, that could be negative if one of these things was pointing in the wrong direction. So actually, if you square that and then square root it, then you've got the volume. And if you think about how it appears, it's the log determinant of k, but it's half log to the determinant of k, so it's log determinant of k to the half. So the term you're looking at there is precisely telling you the sort of volume that the covariance sits on, the amount of space it's taking up. Now, if you know about entropies, the entropy of the Gaussian is log determinant of the Gaussian, so it's also related to the entropy as well. It's telling you how many things that covariance function believes in, and each one of those things is a function itself, right? Okay, it's not a function when we look at it in finite spaces, but it would become in infinite spaces. Conversely, this data fit term is of this form lambda transpose k inverse, y transpose k inverse y. Now again, I've drawn now a 2 curve to illustrate that this is not a Gaussian form, this is now a quadratic well. So we're trying to minimize this term, right? If y was 0, obviously we would have a minimum, because this thing would be equal to 0. But if y is non-zero, so it would sit, so this is y1 and y2, it would sit somewhere up here, up a hill. So this is like a well, a quadratic well. So the way we minimize this normally is, if we want to just, what we could do is we could do a couple of things. If y was observed here, then we could just expand lambda 1 and lambda 2, right? And that would cause that point to come closer to the center, and it would minimize this error. But we typically don't want to do that, because doing that would increase this capacity term. So to do that, you would basically have to say, now this process believes in many, many more functions. So there's a trade-off between these two competing effects. So what actually you might want to do instead is actually increase the correlation between these 2 points. So thinking about what that says is, in that case, we've got lambda 1 and lambda 2. Let's say they were very close together relative to the length scale. So then we've got some other things going on here. So we're looking at y. So I keep saying lambda 1, I mean y. y1 and y2 this is y1, this is y2. They're quite close together, so they're correlated. So the way that so if the length scale was very small initially, then the process would say these 2 things were uncorrelated. But by increasing the length scale, it can cause these things to be correlated, which effectively causes a rotation around of that. I mean, you can't do that move cleanly. Don't get the impression that you can just rotate that covariance, because there's a very complex relationship between changing that length scale and affecting any 2 marginal points of this covariance. So what you want to imagine is that the Gaussian process, when it's doing its fit, is doing this across all data points, trying to correlate them in all these funny ways, in ways that you sort of can't really think about. But if you just think about 2, you can see the sort of things it's trying to do. So it will actually end up sort of, if it can get away with sort of increasing the length scale to represent that point, that's the sort of optimization it might make. So just to illustrate how that might work in practice for a simple toy data set, so I sampled this data set from a Gaussian process, so I actually know the parameters. What I'm showing you here is this decomposition of this error. The blue thing, the capacity term, and the red thing, the data fit term. And then what I'll show you is, as we change, what all I'm going to do is I've fixed the noise value here correctly. So I know the noise because I generated it, and I've also fixed the overall process scale to 1. So that's why standard deviations are 2. So those are fixed, and I'm just going to show you what happens when I change that length scale. So initially, you might think that this isn't very good because these 2 points are thought of as, broadly speaking, independent. Look what happens. The process goes so far out here, it's basically returned to the prior. So the length scale is so small here that these 2 points are independent. As I said last time, I do not think of this as overfitting because the process, it's not fitting this line. That's just the mean of what it fits. It actually believes in functions that are going all the way up and down, but it doesn't know which one. So if you just had one function, then it would go all the way through the data points, and that would be overfitting. But this model believes in infinite functions that wiggle with that thing. So you get these error bars. It's still not a good model, but I think overfitting is an odd term. So what happens is you change the length scale as you increase it, you get better looking fit. But what I want you to pay attention to on here is these curves. So the red curve is the data fit term. So at the beginning, the data fit is actually quite good because it's going through the data like that. But then as you increase the length scale, the data fit term gets worse. But the capacity term, the log determinant, is getting better. So this model here is a bit like white noise. It's getting close to white noise. It believes in lots and lots of functions. Under white noise, anything can sort of happen. It believes in many, many, many functions. But as you increase the length scale, it believes in fewer functions. In fact, if you were to increase the length scale to sort of a very, very wide length scale, it would just believe in a flat function. So this data fit sort of goes worse, but the capacity term gets better. And if you add the two, you get the magenta curve. That's the combination of blue and red. And then you can see that what you get is a minimum. Yeah? So this isn't how we optimize these things in practice, obviously. In practice, we're doing this over a very, well, often not a very large dimensional space, but might be over a large dimensional space, and we do it by gradient methods. I'm just showing you the different fits. So actually the minimum here is at 1. That is actually the correct parameter. That's the parameter I sampled these points from. But of course, it does go up slightly. But notice this curvature here. It's not that certain, right? That's a sensitivity issue. So if you were to do, the other thing you might do in this case is do sampling over these parameters to look at families of distributions, and you can see that it's not super confident about 1. So this fit isn't considered that bad either. It's approximately the same. So there's too few data to really determine the parameters well here because there's only 6 data points. So that's what you can do to sort of find the parameters. You minimize the error or maximize the log likelihood of the Gaussian, which is just the Gaussian likelihood, but you can think about these 2 terms in a separate way. So let me pause there and see if there's any questions about model. Make sense? Question there?
Could you marginalize over the length scales?
Yeah, so we'd love to be able to do that. The question was, could you marginalize over the length scales? So in this case, so this is a negative log likelihood, so to get an idea of the shape of the posterior, you have to now mentally put a plus sign on it and then exponentiate. So you'll see that there's some sort of flattish area here, and then you've got to normalize as well and multiply by a prior. There's some sort of flattish area, and then it also doesn't believe that the length scale is too broad. So it's pretty confident, because it knows the noise. It knows the noise, and because it knows the noise, it's pretty confident that this function isn't totally flat, because it knows the scale of the noise. It's too large for that. So you would really want to be able to, the question, can you marginalize over length scales? You would want to be able to consider all length scales along this line. Now, you can't do that analytically, and the sort of thing people do is they sample. They do hybrid Monte Carlo techniques and take samples. And in low data, you should really be doing that. In larger data, the parameters can become quite well determined and maybe not need to work as much. Other questions? Okay, so it's funny that bit, because normally people think of that thing as looking like a regularization term. Here it's a data fit term. Normally you'd expect the data fit to look like something like y minus f. and then with a square, and then the regularization term would be something like F transpose K inverse F. But here it's Bayesian, so we've integrated over F. F doesn't exist. So once you integrate over F, you get a term like that, which is actually data fit. Okay, so this is a little gene expression example. This is a nice, a student of mine, Freddie Kalitzis, did this to look at some time series gene expression data. So these time series gene expression data is in your cells. You've got 30,000 genes or whatever, but each cell is doing something different. So you can measure the RNA. The RNA is telling you how much each of those genes is being expressed. So for example, you don't produce hemoglobin sort of anywhere apart from in blood. So the RNA associated with production of the protein of hemoglobin is only really present in blood cells. So different cells, different parts of the genome are switched on. And gene expression is measuring that with something called microarray. But it's expensive, so the time series tend to be quite small. So you tend to get time series of 3 points, which is really useless. 2 is definitely not time series. 3, yeah. But you might get 7 points or something like that. And what we're interested in is whether particular time series are noise or their signal. So this is a sort of very simple thing to do with the Gaussian process. And this technique, there's actually nicer ways of doing this, more elegant. But this was so simple and it outperformed a lot of the state-of-the-art when it was applied. So what we did is, let me show you this time series here. I should have had this before. This is a typical time series. Okay? So it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points. We had 30,000 of these and we fitted Gaussian processes to each one. Now the reason this is a cool example to show you is because I scoured through those 30,000, well Freddie did to be fair, and he found ones where this minimization was multimodal. So this is an example. So what we're plotting here is now the two-dimensional optimization surface. We can do it because the scale of the process, so there's 3 parameters, right? Noise, length scale, and then the overall scale of the signal. But we can actually convert the parameterization to a to a signal to noise ratio, which I've shown here on a log 10 scale. And then we can optimize the remaining parameter for each of these points. So every time we go to a point here, we find a unique optima for the remaining parameter. So that gets us down to 2-dimensional space. And what I'm showing you is length scale here and signal to noise ratio here. And what you're seeing in this surface, so red is good. So what you're seeing in this surface is actually there's a minimum here, but there's another minimum here, and then there's a ridge up here. So you see these are not unique maxima. I mean, we had to search through 30,000 genes to find one. This isn't very typical even for relatively low data, but it can definitely happen. And then what I'm showing you now is some of the different optima. So this one was a length scale of 1.2. So this is, oh, that's funny. So that's in minutes. So I guess the length scale must have been in hours or something. That's a bit confusing. But anyway, the length scale parameter I have here is 1.2 on this scale. So that means it's somewhere up here. And the signal to noise ratio is 1.96. Oh, so that means it's all the way up here. So this one is where it's saying that it's very low noise and high signal. And this is one of the optima it's found. It's not even on the chart. It's a very high signal to noise. Okay, so that's an optima it's found. But would we say it's a good optima? Well, I don't know, but look at the likelihood. Remember that likelihood, it's minus 0.22. This one here is signal to noise, length scale of 1.52, so this is here, and then signal to noise of 0.21. So it's around about here somewhere. So it seems to be this minima associated here. So this one is saying, oh look, it's a lot of it's noise, but there's some signal there. And then this one here is a likelihood of minus 2.1. So this is very bad likelihood, and a signal to noise ratio of minus 0.45. So this is all the way down here and over here. So this is the sort of flat solution. It's just fitting it with noise. So there's some sort of plateau effect here, which it struggles to get out. So with lots of restarts in this space, we found each of these solutions. But this solution, so what we were interested in is whether there's signal. And what we're actually seeing is a point here and a point up here. Now notice that this point here is minus 0.23 and the point here is minus 0.22. That's near as damn it the same, actually. remember the likelihood's in gnats, so this is e to the 0.1 difference in terms of probability. So there's a family of solutions all the way down here, which it can't differentiate between. So there's an uncertainty there. This is one extreme end, and then this is the other. But for the purposes of that paper, we didn't have to care, because we knew that the signal thing was more likely than the no signal thing. Yeah? So we could use that and then say, we don't have to sample. Strictly speaking, if you really wanted to know what was going on, you could sample up and down this ridge. But in that case, we didn't. We just said, okay, there's signal, there's no noise. And then we can say, keep that gene in. So something's happening for that gene in this experiment. That's what you're interested in. Are you just observing noise, or are you just seeing an actual signal? So this one is an interesting example. I mean, if you look at it now, it's not that clear whether it's noise or a signal. Actually, that could be an outlier, couldn't it? So there's a vulnerability of our method. But overall, we perform better with this thing. Okay, so I sort of mentioned at the beginning that these models are related to basis function models. So I just want to give you an overview of how that comes about. So typically, if we look at basis function models, what we do is we have a set of basis functions, and a neural network is just a basis function model, going into another basis function model, going into another basis function model. So here, I've taken a sort of set of basis functions, 3 basis functions across some input space, and then I make predictions by doing weighted sums of these basis functions. So basically, I sort of put weights on each of these, and I say, okay, the final function, if it's high here and low there, is 1 of those, 0 of those, and minus 1 of those, something like that, right? That's a basis function model. So that's a parametric model. So that's the sort of form we might write down, and then we have a set of parameters for those sort of models. If we want a standard linear model of basis functions, if it's a high-dimensional input, basis functions are just those different inputs. So this is a sort of a variation of a multilinear regression. Now, what I want to sort of look at is what it looks like if I sample these weights from a Gaussian. So if I sample these weights from a Gaussian, I get something that looks like a functions, right? So this is, before I was sampling functions, here I'm sampling weights, but you can sort of see in these things that you get, you know, okay, this one's clearly got 3 positive weights, this one's got a negative, a small, and then a positive, and this one's got small, small, and negative in the middle. So we're sampling functions, but we're now doing it through these weights instead of directly from the covariance. Okay, so we'll look at some little properties of Gaussians, which will let you see why that's in the end a Gaussian process. So some of Gaussian variables is also Gaussian, right? So if I know that yi is distributed to Gaussian according to something with a mean ui and a variance sigma I squared, then the sum of all those yi's is also Gaussian with a sum of the means and a variance the sum of the variances. Now this is very unusual. Okay, so it works for Poissons. Poisson distributions, if you do sums of Poissons, they're Poissons as well. It works for gamma distributions. I can't think of another example at the moment, but both those, when it works for Poissons and it works for gamma distributions, both those distributions start looking like they're Gaussian distributions because of the central limit theorem. So this thing, if I replace this with any other distribution, as long as it has finite variances here, then the sum would be this thing, eventually, would tend to this thing. Okay? So this is one reason why Gaussian processes are quite powerful, because of that. So that's a very special property of Gaussians. And then this other weird property, which isn't weird at all, is that scaling a Gaussian leads to a Gaussian. So this one here says, well, if y is Gaussian distributed, then wy would be just scale the mean and then scale the other side of the variance. So that's not that weird. But then this has a consequence in the multivariate case. So the multivariate consequence is that if I have x is drawn from a Gaussian like this, and then I just say y is wx, where w is a fixed deterministic matrix, then y will be a Gaussian with a mean of w mu, and then the covariance of this form. So this is like the generalization of this equation here, in the scalar case. But it relies on the sum of things being Gaussian and the scaling factor. Like if you do this for other distributions, this will be true of the covariance, but you'll leave the class of distributions you were originally in. So this is sort of an unusual thing. So this is an unusual thing, and it's also, Philip Hennig at one of our GPS summer school things made a really nice point, which other people have made before, but he made it very well, that this is just linear algebra, right? So if you make a linear algebraic operation on something which is Gaussian, you just get something Gaussian. Computers are really good at linear algebra. So this is one reason why Gaussian processes are quite powerful, because if you stay within these domains, these quite advanced actions, which this is a marginal distribution computation given a prior. This is another way of looking at it, and a sort of likelihood, although we're not corrupted things here. And this is normally a very headachy operation to do. You've got to do sampling or something like that to do it. But here it's trivial. It's just linear algebra. Okay, so it turns out that if we apply those ideas, that we can show that the covariance function associated with these basis functions is just given by this inner product. This is kind of what Arthur was sort of saying, probably with the kernels at some point. He's talking about these Hilbert spaces, and the Hilbert space from the perspective of the Gaussian process is the thing that comes in between these two here. So this is a finite dimensional case, and you can look at the covariance function, and what you see is that the covariance function, okay, it drops off to 0 because these basis functions don't exist at these points on the real line. But in the bit where it's present, it looks a little bit like that covariance function we had before. So, on that. Oh, that appears twice, just for memory. Now, the interesting question though, if you're doing a basis functional model, and this is true for a neural network as well, you're faced with these two questions. What are the locations of the centers? Or for other basis functions, what's the scale of the input or whatever? And what's the number of basis functions you should use, which in a neural network is the size of your different hidden layers. Now, what I'm going to do is I'm going to restrict the analysis of this system to 1D inputs, but this works for high dimensions as well, and then I'm going to consider uniformly spacing these basis functions over a region. They don't actually have to be uniformly spaced, but it just makes this little analysis simple. And what I want to do is look at this form of this kernel matrix here, and show you how this sort of thing turns into the Gaussian process we saw before. Okay, so this is the form of the covariance matrix, and then we can rewrite that as a sum over some exponentials of the basis function in xi, so it's kxi xj, times the covariance function in xj. Now, if you've seen Gaussian stuff before, you should immediately realize this is why Gaussians have all these interesting properties, because the multiplication of two exponentiated quadratic forms allows you to bring the quadratic form inside, like this. So you don't leave the class of distributions. And this is why everything keeps staying Gaussian in the Bayesian case, because you've now got a quadratic form inside here of this form here. So this thing looks like, that wouldn't normally happen. So when you do this with a neural network, so if you do this with like the rectified linear units or a hyperbolic tangent, at this step you immediately leave the class of functions, and you have much harder integrals to do. But you can do it for those models as well. So this uniform spacing over a region has allowed me to write the mu k, and what I'm going to do is replace it. So mu k is the center of the basis function, and I'm replacing it with a, the starting point of the first basis function, plus delta mu, which is the gap between them, times k minus 1. I'm obviously doing this because later I'm going to take k to infinity, right? And the gap down to 0. So I'm going to turn this into an integral. It's because I'm going to have infinite basis functions. So expressing these basis functions sort of in terms of their indices and putting in the k here to replace the mu k, what I can do, I'm going to scale, oh, and I also have to scale, yeah? So I have to pre-scale the whole process by this gap. Because if I don't, then as I add more basis functions, the scale of the process goes up. So this corrects for that. I make a few substitutions. So I decide that the first basis function is centered at A, and the last basis function is centered at B, so that if I've got m basis functions, I have B is equal to the sort of mu m. I'm going through this fairly quickly, but you can see it in the slides. And then that allows me to sort of realize that m, the number of basis functions, is given by that interval divided by the delta mu plus 1. So obviously now I can say, okay, I'm going to take delta mu to 0, and I can scale m up to infinity. And once I do that, I get this integral replacing the old sum. So I'm just doing that old sort of trick of taking the discrete thing, which is now multiplied by delta mu, and returning that to infinity. So, and we're using the fact here that a plus k times delta mu is mu itself, it's the variable mu. And now I need to integrate over mu. So I'm now convolving these Gaussians all over their inputs over the input space. And this is what the result of the integral is. So the first part of this integral is this. That looks exactly like the covariance function we had before. That's the GP, that's the exponentially quadratic covariance. And then I've got these two other terms here. Now they look a little bit complicated, but they basically have the same form. One's the negative of the other. This is an function, which is the integral of a Gaussian, of centered at B, around these variables. And this is the function centered at A around these variables. So the effect of these two functions is actually to squash off the ends. Because remember, we started putting in basis functions at A, and then we put other basis functions in, we stopped putting them in at B. So in the next step, what we can do is we can say, actually, let's put them all over the real line. So we'll take A to minus infinity and B to infinity, and these two terms just turn into 1. And we recover that. So notice the only difference between that and our original function is that we've got a 4L squared. So there's some sort of square root of 2 on the length scale. So the length scale we see, this is our exponential quadratic. Oh, and we've also had this scaling in front, which is associated with the length scale. But if we sort of reset alpha to be this, and if we reset L to be the square root of the length scale we saw in our standard process, we get the same thing as we saw before. So sort of an RBF model, these radiant basis function models, they used to be all the rage back in the 90s. And people still use them, there's some sensible reasons to use them. If you take it with infinite basis functions, then you recover this as your covariance function. And now this is actually doing the operation that I think Arthur will have talked about a lot, about moving into Hilbert spaces, the sort of other way around. So this feature space is really infinite dimensional Hilbert space with all those Gaussians, right? But we haven't really used the maths that they tend to use in RKHSs to come across that. We just use an integral. But that's not the only one, right? So we can do this for a number of covariance functions. But going back to, just to re-emphasize the point, this is why it works, right? It works if everything stays Gaussian because the product of these two things is sort of Gaussian. Everything stays exponentially quadratic because the product of two exponential quadratics is an exponentially quadratic, and the integral over one of those over a parameter mu is also an exponentially quadratic form. No other covariance function looks like this, looks like its basis. So there's one for sort of hyperbolic tangents, and it's in the form of an arc sine of something unusual, right? So it doesn't normally work out like that, and normally the integrals to do this are quite a lot harder, so you can't always do this with your particular favorite basis function. Okay, but what that's telling you is that the Gaussian process, so that's what I've been emphasizing, the Gaussian process is a basis function model where you remove the need to decide on the number of basis functions and their location by saying, I've got infinity of them, and they're everywhere. Certainly for this model. Okay? So that's nice, because we don't have to worry about hidden layer units. This is why we started using these models back in 1997, because they also sort of perform better than neural networks for the sizes of data that we had back then. And at that period, there's some really nice work. So if you're interested in this further, I would still recommend reading Radford Neal's thesis. Radford Neal did some lovely work on Bayesian neural networks, and he was the one to realize that if you took a neural network and you took the limit as the things, because of the central limit theorem, they converge towards Gaussian processes. So, and then Chris Williams developed a number of different covariance functions from neural networks and said this is what the covariance function underlying a very wide layer neural network is. So they have these sort of nice theoretical properties as well that makes them like neural networks. So these two are related. Of course here, we don't have basis functions, we've only got 3, and they're over a fixed line, but if you can sort of picture in your head, then that being, those basis functions being moved out, then it doesn't surprise you that you end up getting that sort of form of covariance function. So this here is the neural network covariance function. So if you, it's not hyperbolic tangents as your activation functions, it's Earth functions, probits, because that makes the integrals tractable. You can't do the integrals with hyperbolic tangents when you take the product. So this thing here is the neural network basis, right? So it doesn't look anything like a probit in the base case. It's got this weird inner product form with some normalization, and then it's an arc sine. It also has this effect here that it's not stationary. So there's something here in the middle, but then it starts going out at the sides. The variances are increasing as you go out. And this is the sort of, This is the samples you sort of get from that type of covariance function. So notice actually, the variance is not increasing, they're saturating. I shouldn't have said they're increasing. They'll saturate as you go out. Because what this model is saying is put a load of sigmoidal shapes, and in this case, we haven't put them all across the real line, we're putting them in the middle somewhere. So as you leave the region of activation of those shapes, you tend to saturate at a fixed line, just like a neural network would. So the interesting thing about that is that this is giving you the correlation that you believe in between your data points, but it doesn't look anything like those activation functions. So it's a very different way of looking at what your model's doing. Now you could do lots of things with covariance functions because of the properties of Gaussians. If you want sort of sum two covariance functions together, then that's also a valid covariance function. And it's just the sum of the underlying processes. So if this is Gaussian process F1 and this is Gaussian process F2, summing those two processes together gives you this new covariance function. That's really nice. In any additive model, you can do lots of things with that. The product of two covariances is also a covariance function too. It's less clear what this means physically, but that's a valid thing to do as well. People use that for building temporospatial models. If g of x is a deterministic function and f of x is a Gaussian process, so you sort of, for some reason, you've got a Gaussian process, but you know it's multiplied by some deterministic function, then you can easily show that the covariance function of the process h, which is the product of the two, is just given by g of x, kf of f, g of x prime. That's really useful. So if you've got a non-stationarity, so one way, someone asked me about change points the other day. So if you've got a non-stationarity in your model, these processes are stationary. But you can use those two things together to sort of squash one of these processes out. So you can switch processes. You can have like a squashing function that switches one process on here and another process on here. Right? And then you can sort of construct the covariance function such that it smoothly switches between them. And then you can search for the location of that for a change point. So that's a really elegant idea, and it was quite widely used, I think that's how they do it in the Automatic Statistician from Zub and Garamani, where they sort of change covariance functions across the input of the data. So the linear covariance function. So this is a very long-winded way. If you actually build, so you should try this if you are interested in GPs. Build this covariance and sample from it, and you will see some straight lines. It's a very long-winded way of building a straight line model. You can actually consider that just sample W and look at what it does. But it makes sense, right? When you think about this, the marginal variance along here, it's of course quadratic. So the marginal standard deviation is going to be linear, and it's anti-correlated. So this is sort of negative, the same value of, at the far end, this is negative, the same value of that. This is 1, and that's -1. Yeah? So it's something that's 100% anti-correlated across the 0 point, and therefore it sort of makes sense when you reverse diagnose it that this is what's going on. Now, I'll just pause to say something, because people have brought this up before when I present. They sort of say, why the covariance function? I would agree fully that the covariance function is not always the most interpretable thing for understanding your model. Okay? So this linear model, if I gave you this covariance function, then you might take a while to understand what's going on. You'd work it out eventually, but it's much easier just to say f of x is equal to w times x, right? But why we use it? Because it's the universal language of these processes. So you can express Gaussian processes in terms of their Fourier spectrum for some processes. You can express some processes in terms of Gauss-Markov process, which is what I think I'm going to do next. You can do all sorts of things, and they're very interesting, and sometimes they give you a lot of intuition for what's going on in the model. But if you want to bring two processes together, additively, you have to do that. You have to express them in terms of their covariance function. Because the covariance is the sort of, it's the API, to use computer scientists speak. I mean, API as in software entry into a Gaussian process. It's how a Gaussian process speaks to other Gaussian processes. Okay? So at some point you need to go into this thing, and it's the most general form. So all Gaussian processes can be expressed in this form. Certain Gaussian processes can be expressed in other ways. They may be algorithmically more efficient, but it's not the most general thing. Okay, so like the basis function model is a Gaussian process, but you can do it quicker by considering it as a finite process. So the limitations we've already mentioned last time, to do inference with this covariance function form, if you express the process that way, it's going to be n cubed, which could be very heavy. They don't deal with discontinuities very well, because that's not Gaussian. Now, let me back up a little bit from that. Gaussian processes are sort of non-parametric models. What do I mean by that? I mean that once you've expanded it into that infinite basis functions, you cannot summarize what your training data is doing in a fixed number of parameters. If you add a new training data point, you have to increase the size of your parameter set. That is a very, very good thing, because it means that when you design the model, you don't have to know how much data you're going to look at. And it's called non-parametrics, Bayesian non-parametrics, and it's a good thing to do because of that. Now, if you've got discontinuity, so let's say we've got a discontinuity in our function. So we've got some sort of function like going on like this, and then the Argentinians default on their debt, or I don't know, Vladimir Putin invades Ukraine, something like that. That's a discontinuity. So actually, stock markets look very much like Gaussian processes until someone does something silly or sensible, but that the markets don't like. You know, let's not judge what they're doing. And then they sort of carry on like this. Now, this thing here, this is why we had a massive financial crisis, because everyone was modeling things as Gaussian processes, and those processes did not take into account these sort of things can happen, because it's jointly non-Gaussian. These things are all jointly Gaussian. A big jump like that would mean a sort of heavy tail in the process distribution. So it's not going to happen. Now, you can put these into your process if you know where they are. So if you know this is going to happen on Friday, you can put it in a mean function, or you can use deterministic functions combined with your covariance to deal with it, right? So that's okay. That's fine. If you know when they're going to happen, and you know how many of them are going to happen. But once you've done that, you know, if that's like, so this is sort of time 1, and this is time 3. Let's call them mu instead of time 1, and mu 3 instead of, and then mu 2. So you know all those things. You can put them in your model. You can do that. That's fine. But look what's happened. These are now parameters of your covariance function. And you've introduced parameters in your covariance function to say when these things happen. So you've sort of started moving back towards a parametric model. I mean, it's still non-parametric in some sense, but you're starting to add in the disadvantages of a parametric model, because now you don't know when these things are going to happen. So what you really want is the ability to sort of know that one of these things could happen with some finite probability at any given time. So that's like a Markov jump process. But if you combine a Markov jump process with a Gaussian process, you get something called a Levy process. And the problem with them is you can't write down the likelihood. So you can only express them in terms of the characteristic function. So because you can't write down the likelihood, you can't fit them to data. So that's why we don't use them. They would be great, but you can't fit them to data easily. I mean, you have to do something odd. It isn't one of the standard things we use. So putting in discontinuities is very difficult. So financial crises, phosphorylation in computational biology is when, often quite quickly, one kinase, or sort of one transcription factor, one protein, changes its form by having a phosphorus thing attached to it, and then changes its role. So that looks like a discontinuity. Collisions. So if I walk into this wall, then I don't act as a Gaussian process. I sort of rebound quite rapidly. Or even my footfall on the ground is actually involving a collision. So that's if you're trying to model sort of motion capture, Gaussian processes are fantastic for modeling flying birds, but not so much for modeling, I mean, we do it, but there's problems when the feet hit the ground, right? Edges in images. If you're thinking about the Gaussian process as being the image as being a Gaussian random field, which people have done, then you have trouble when you get to an edge, because that's a discontinuity. And actually as well, this exponential quadratic that we've been talking about can be way too smooth in practice. So remember I said I was rude about people in signal processing saying that they use this band-limited things? It's for very sensible reasons. It's not sensible in machine learning because it's excluding the possibility that there's high-frequency signal. And that's really a bad idea, to sort of exclude the possibility of something, because then your model can never see it. It's a sort of variation of Cromwell's rule. So it was called Cromwell's rule by a Bayesian statistician called Dennis Lindley, and And it comes from, apparently Cromwell was writing to the Scottish church, and he said, I beseech thee in the bottom of your hearts to maybe believe that you're wrong, or something like that. And he's sort of saying, there's always a possibility you're wrong, so you should never exclude circumstances. I think it's ironic because Cromwell wasn't really, he's seen as a man, certainly not by the Irish, as someone who was constantly questioning himself. But there you go. Cromwell's rule. Don't actually exclude things. But the exponential quadratic doesn't exclude high frequency, but it suppresses them. It suppresses them a lot. So it's infinitely differentiable, which can be a very bad idea in one dimension. So you typically move to other things if you're using one dimension. So in the last, let me just pause there before I move on to sort of how the Kalman filter. So probably all, this is, what is it? It's 20 to 6. Listen to machine learning talks all day. So let's just pause and see if there's any questions about that bit. So I've sort of tried to relate to you how a Gaussian process is related to sort of basis function models. Neural networks are special cases of basis function models because you tend to move the inputs, the location of the basis function, you optimize them. So that's like optimizing the parameters of your covariance function. It's like a covariance function with a load of parameters in it, which is why the optimization is so difficult, much harder than the one I showed earlier. So questions at that point? There's no question, and I'll just, I'll probably have to overrun, realizing that
So at your graph there, with your discontinuities, kind of zoom out enough, and you observe it for long enough, then that's what I got.
Yes, thank you. Did I plant that question? Did I pay you some money? Yeah, no, excellent question. So the sort of thing that you get asked is very often, well, what about when the world's non-Gaussian? And the question is absolutely right. If you zoom out over time, over a long enough time, if you stop micro-sampling the stock market, and you sample it over a month, not a month, over 50 years, then the number of these crises start adding together. You get 6 or 7 of them, and it returns to a Gaussian process. So this is why, this is something that fascinates me actually. That fascinates me because it's one reason why things are converging towards Gaussian processes is that. They don't converge towards anything else. If you zoom out at the time scale, then it looks like a Gaussian process again. But this also implies something really interesting, which I think philosophically is very interesting. I've not really seen written much about. It implies that you can sometimes, I guess some people write about this, but it shows you that sometimes you can be better off not collecting more data. If we wanted to model the stock market as a Gaussian process, we would be better off sampling it every 30 years. And then the Gaussian process would fit nicely, and the error bars would be well calibrated. As soon as we start collecting too much data, we get happening, now I have to go way back, exactly what we showed. It was here. Exactly what we showed here, bang on, there we go. Oh no, it was the one before that, wasn't it? We get that sort of thing happening. So equivalent to this sort of question is, well, let's look at the noisy case. So if we're sort of subsampling in here, then these error bars might be well calibrated, probably not at that point because they've used to the noise. So let's go back to the other one, so it's better to illustrate on the other one. At this point here, if we don't sample regularly enough, then maybe these error bars are well calibrated, even though the model is slightly wrong, because as you pointed out, okay, so it can be a discontinuity, but if you look at a long enough scale, those discontinuities collapse back to being a Gaussian process. But as we start to get more and more data involved, then the model becomes wrong again. So that's sort of interesting. I think it's a good point, and it's true that it will converge towards a Gaussian process, but you try, I haven't tried, I have spoken to some financial companies. I've never tried telling them that the right answer would be to stop trading every microsecond and to sample the market every 30 years. And, well, there's something in that, isn't there? Because if you think about like all the really powerful institutions, like they invest over very long periods. That's how you get very rich. You buy shares in 1750, and then you just hold on to them. Well, maybe they disappear, I don't know. You invest in the market in 1750. Okay, so let's get back to here. Other questions? Okay, so that actually relates a little bit next to the next part. No other questions? Good. So the final thing I want to do probably is introduce how Kalman filter is a Gaussian process. So Kalman filter is a model. So they're new models used in tracking. So the Kalman filter, most extraordinary. The Kalman filter was used to get us to the moon. I love that about people who believe, conspiracy theorists who believe that we didn't go to the moon. They sort of neglect the fact that we invented all this technology to not go to the moon in an effort to appear like we were going to go to the moon. And the Kalman filter is one of those technologies. So they track the moon using a Kalman filter. And it was introduced by a guy called Rudy Kalman, and it's a sort of discrete time model. So what you sort of say is, you start with a Markov chain. So you say that your location at any given time, this isn't your actual observed location, this can be a latent location, is given by your location at a previous time plus some Gaussian noise. Okay? So that's saying that's Gaussian noise. So we can write that down probabilistic like this. Now, this is a very good way of writing down a process. So there's two sort of principal ways you'll see people writing down processes. One is Markov processes, certainly in time, and the other is Gaussian processes. So the two things we've written down here, this is called the transition distribution between two times, and this here is the initial distribution. Okay? So those two things uniquely define a Markov chain. So remember that quote from Laplace? So Laplace was 100 years before Markov in saying it, but the state of the previous state of the world at the previous state and the present state is given by the state before, plus some change. And then the change is Gaussian in this case. So in the Markov chain that we're interested in, to make it a Gauss Markov chain, we have a Gaussian initial condition and a Gaussian transition. And so what we're saying is something like this goes on. So this could be like, you're trying to track the spacecraft going to the moon. You don't actually use this directly. You're trying to infer what your coordinates are, and you're assuming that your coordinates are changing at each point in some sort of Gaussian random way. So that's got a sense that that should be a Gaussian process. If this point here corrupts that point with a Gaussian, and that one does the same here, I've not put an initial distribution, I started at 0, then these things should be jointly Gaussian, because the sum of Gaussians means that that is Gaussian distributed away from that. Everything's Gaussian distributed away from another. So the question is, what is the covariance function of that process? Well, so this is where we can use these little tricks. So the reminder is that if Z, now I've used instead of X, is drawn as a Gaussian in this form, then X would be given by W times that plus B, and then that would say that X was also Gaussian distributed. So we can construct the covariance function of the Kalman filter using that rule. So that's a simpler version of the rule. So if Z is spherically Gaussian with sigma squared and X is WZ, then this thing here is going to be 0 mean, if this was 0 mean and that was it. So if that's not adding anything and that's 0 mean, WW transpose times sigma squared, which has come out the front. So if we look at the Kalman filter I showed you before, what you can see, so if we say that x1 was equal to x minus 1, which was x0, which is 0 according to the thing I showed earlier, plus the noise, then x1 is equal to 0. x2 is equal to what was x1, which is just epsilon 1, x1 is equal to epsilon 1. What was x1, epsilon 1 plus epsilon 2, so on and so forth like this. So what we can see is that the observed form of our process is equal to a lower triangular matrix times the noise vector there. Now we've done that, we've got the thing in the form we need to write down what the covariance is. Because we're saying x is L1 times epsilon, and we know the covariance of epsilon. So that's the model. Okay, I keep meaning to take this bit out because it's more complicated than I need. But what it tells us is the covariance, which is also because it's 0 mean, the expectation of x transpose, is now just simply equal to alpha. We've pulled that alpha out, L1 transpose, which is equivalent to the sigma squared W transpose. So that's the covariance matrix of this finite set of points. It's not yet a process because it's not continuous, it's discrete. And so we've been interested in, we might want to make these things continuous because discrete, the reason Kalman filters were used to go to the moon is they actually built a digital computer to go to the moon. So the lunar landing module was a 16-bit digital computer built in the 1960s. Absolutely extraordinary. So they had approaches, they had a discrete time linear filters. They also had to invent, if people know Kalman filters, they'll know that in practice you have to use something called square root propagation to maintain numerical stability. That was invented because they realized that they wouldn't get to the moon, they would lose numerical stability on this filter if they didn't change their algorithm. So it's very cool how much was invented for going to the moon. So this is basically the equation. The x, which looks like a process, is zero mean with this covariance matrix. It's not covariance function yet because we haven't turned it into a continuous thing. So, now, what I want to do is turn that into a continuous thing. So what I'm going to say, so I'm going to make a little bit of assumptions. So if you can turn it into something continuous, instead of having a variance that is basically finite for each interval, I'm going to make the variance a function of the interval. So make the variance dependent on time interval. And actually, I kind of have to assume the variance grows linearly with time. Nothing else would make sense. Because if I go to 2 time intervals, 3 time intervals, I'll see it sums with time. So it's not even an assumption, that's just the truth. The variance will grow linearly with time because of the sum of 2 Gaussian variables being Gaussian. So you get this additive variance over time. Now, if I do that, then what I'm doing in effect, so the variance of that, so that's the variance of the jumps, which was given by alpha. So I'm saying it's proportional to the time interval. So the smaller the time interval, the smaller the variance. Obviously, if it's delta t is 0, it's 0. If delta t is 2, then it's 2 times the original variance, which matches with the original process. So if I say this, I'm just using this trick to bring in to the time again, and I can turn this into a continuous time model. So what I want you to recognize is that in this matrix here, the I, jth element of this matrix is just given by alpha delta t times the inner product between the ith row and the jth row of L. But this inner product between the ith row and the jth row of L is quite simple to work out, because L is a vector from the triangular matrix. So the kth row of L has the first k elements being 1 and the other elements being 0. So when you take an inner product with that, with another row vector, you just get the minimum of I and j out. So you can now rewrite that as the minimum of I and j. So this covariance function, this operation here, is just the minimum of I and j. And now we can also define as the delta t times I as time, and then that just pulls through because the delta t can come inside this minimum. So it pulls through into delta ti times delta tj, so we've got the minimum of ti and tj. So that gives us the covariance function. So we've got continuous time covariance function. This is actually the covariance function underlying Brownian motion. So that was derived originally by Einstein. Einstein's assumption for Brownian motion was that you've got a stochastic differential equation where you've got your, it wasn't actually a pollen particle, it was a particle inside some water within a pollen particle that was moving around, and then water molecules are hitting it. And so he assumed that you've got white noise approximates how those water molecules are hitting it. So this is the form, so the covariance, so it's 0 here and it grows linearly. So the marginal of the variance grows linearly. That tells us immediately that the standard deviation is growing as the square root of time. And that's known for Brownian motion, that a random walk, as it's called, will grow the standard deviation with the square root of time. So this is the sort of thing that these processes look like in practice. Notice they're not smooth at all. There's no smoothness. They're not discontinuous, but they're not differentiable. So this is the sort of thing people normally expect when they see Gaussian processes. So that's sort of interesting, isn't it? Because actually, that's the model they had, in effect, for the lunar, well, so the lunar thing and the command module's route to the moon, they were modeling it as a random walk. And whenever someone is using a Kalman filter, that is what they are modeling it as. This is really interesting. If you take that covariance matrix and you invert it, so I advise you to do that as well. Compute that covariance matrix, and then do the inverse, you'll see this. This is a sparse matrix. It's got zeros everywhere here and zeros everywhere here. It's got a diagonal present, and these off-diagonal elements are negative. Why is that? Can anyone tell me why you get that?
You can take that as a previous matrix with 0 to 1 in diagonal?
No, the previous matrix is full. matrix is full, but the inverse matrix is sparse. Pardon? Because of Markovian, but yes, so it is because of the Markovian, but what property of, why do we see that in here?
It's in because it's a function of only its current state, so the next times it.
Yeah, so what, but yeah, so you're struggling, you're both, I think, going to get the same thing, but I think that the word you're looking for is conditional independencies. Do you remember when Bernard said at the beginning that you're interested in causality and conditional independence structures? So if you've got a graph, a Gaussian random graph, the conditional independence structure manifests itself in the precision matrix, not the covariance matrix. So remember we said that there's a number of different ways of representing a Gaussian process. So one of those ways is to specify the conditional independencies. So you sort of have a graph here, and then you say, okay, well your diagonal is always going to have something in it, because this has to be positive definite. And you say this variable is related to this one to this one, so on and so forth. What you mean by this is they're conditionally independent. What you're saying is you've got some form of graph structure, perhaps like this. And what you mean by this is that this one is conditionally independent. So if this is x1, x2, and x3, I'm not worried about you reading it on the side because it's so far away you can't read it anyway. You're specifying a model in terms of probability of x1 given x2 and x3, probability of x3 given x1 and x2, and probability of x2 given x1 and x3. That's what those links mean. If that's how you specify the model, when you take the product of those Gaussians and work out what it looks like, you'll find that the inverse covariance matrix is sparse. The reason is because when you write down the product, the covariance appears like this in the inverse. When you write down the product of all these Gaussians, right, you've got this sort of sparse structure appearing here. The sparse structure stays, but this is the inverse covariance, because it appears in the exponent as a sparse structure. So you always get this sparse inverse covariance. What we did in our Markov chain example is we made probability of x2 given x1. I derived it in the way you would not normally derive it, because I derived it out of the covariance. But I wanted to do that to illustrate this point of conditional independencies. And then you see that conditional independence on the inverse. Now this is very unusual, because for most processes, most things where you specify conditional independencies like that between data points are not valid processes. They're discrete Gaussian matrices. In this case, it is a valid process. So it's a Gauss-Markov process, and it's funny to derive that. You sort of know, the first time I did that, I knew it was going to be true, like, because you can do the maths, but you don't really believe it's going to be true, because it's got this full matrix, you're going to invert it, and then it comes out all sparse. It's one of those magical moments. So if we look at the RBF, does this freak anyone else out? This totally freaks me out, this colour plot here. I'm slightly colourblind. Not that badly. I can tell you're all sitting on green chairs. No. Look at this. Oh, it really freaks me out. I can't look at it. Look at the bands down the side here. Yeah, so this is the inverse covariance matrix of the exponential quadratic curve. And you could prove that exponential quadratic can never be represented as a Markov process. It's infinite order Markov. There is, in theory, an effect from the beginning of time. Of course, in practice, it's so small it disappears. But that means that you don't get the conditional independence structure here, in this bit that's freaking me out. See these yellow bands? That's what makes me feel slightly ill, the yellow colours. Isn't it a bit stupid to make slides that make you feel ill? But I couldn't bother to change the colour now. But you sort of see the central structure looks the same, but then you're getting additional parameters going out. So that inverse is full. That's the reason why Kalman filters are efficient and these models aren't. Because in a Kalman filter, you can exploit that sparse inverse. So when they do square root filtering, they're effectively exploiting the conditional independencies to do it fast. And it's when you do these conditional independencies and propagate uncertainty through, you have to use Cholesky decomposition to keep it numerically stable to ensure you actually reach the moon. Okay, but that isn't actually a Kalman filter, because what you do with a Kalman filter is a little bit beyond that. So in a Kalman filter, and this is a simple Kalman filter. I mean, who's had to study Kalman filters here? Theoretically, you poor people. I mean, I think if you actually do an engineering course on Kalman filters, it's just a nightmare. I mean, I've tried to read the books, and it's like an entire 10-week course, and at the end you still don't understand how the damn thing works. That's because every one of these matrices has a name. in the Kalman filter. So actually the more general Kalman filter, those transition matrices over time could be not sort of independent Gaussian. You can do all sorts of things. And if, I don't know, there's the Kalman gain matrix and all these sort of things. If you look at it from the probabilistic perspective, they have quite simple roles, and they're either posterior covariances or prior covariances or something like that. And then you could ignore the full Kalman filter course and just think of it as some form of Gaussian process, Gauss-Markov process. So, if we assume that we've got a queue of these processes going on in the background, so it's not just one, there's a queue of them, and we're going to assume they're independent. So in a general Kalman filter, you might not assume that, but it doesn't matter. We're going to assume they're independent. Then we've got this prior distribution for what those processes are doing, and there's now a vector prior, so so each one of those processes is given by a Gaussian process with this covariance function that we've just been deriving. And now we assume that we make observations that are related to those latent variables by another matrix. So this would be in a hidden Markov model, you would call this the emission probability. So it's saying that what you actually observe is equal to some corruption or some affine transformation of x. And you'd probably add some noise on here. But we don't need to add the noise because in the Gaussian process you can always do that at the end, right? Because it's just add the covariance function. So I just want to focus on this. So now, what we can do is introduce a Kronecker product to represent this. So if we stack those processes, so each one of these is a time series, and we stack them one on top of each other. This is kind of what you have to do if you're going to do multivariate systems in a Gaussian process. Then we define x to be the vector of all those time series stacked on top of each other. Then we can give the Gaussian process for x over multiple processes now as being given by this form here, where this is a Kronecker product. So who's seen Kronecker products before? Oh, good. So I've got some slides on what the Kronecker product does. So this is what a Kronecker product does. It's like a tiling operation, a weighted tiling operation. So the first thing is the weights, and the second thing is the tiles. Yeah? So it turns this object here into a matrix here. So if I made this I, the identity, then I just get k and k. So I'm saying things are independent across each of those processes. So I being the dimensionality, so this is you can do this for whatever dimension you like on the side here. So I being a very big thing, which is however many latent processes q, then we get, okay, so I've done it in colors here as well. Yeah? So you sort of see the structure there. So if I do that I times k, then that's giving me that independence, but writing it down in one Gaussian density, which is what I need to do to apply the magical rules of Gaussians that we learned earlier, the multivariate properties, because that's how we're going to derive the Kalman filter. So that's what what's going on here, is what I'm saying is that this thing here is the min of ti tj, and then what we're saying is if we multiply it by I, then we get this object here. So independent processes with these being 0, of the min ti tj. Yeah? Make sense? Okay, so now I'm going to pull a trick. I said we stack x, which I think of as the columns. So I always think, so in statistics it's called the design matrix if you put your data points, each data point in a row. So each time series is a column of my matrix, x, that I'm going to stack. But of course I could have chosen to stack the rows. So I could have chosen to stack each of those rows on top of each other. Now if I choose to stack the rows on top of each other, the effect on that covariance is, okay, so the marginal distribution for 1x looks like that. But if I choose to stack the rows, I get this Kronecker k cross I. So now the I is being tiled weighted by k, right? So if I do that operation, and I look at the picture, now I get something like this. Make sense? And now if I look at the marginal distribution of one of those rows, I see they're independent. Because I said at the beginning those rows are independent. So just that flipping, so mentally, whenever I think about these things are tensors, they're everywhere. I mean, it takes you a while to get on top of them, but actually once you get an intuition for them, they're quite easy to handle. It's like linear algebra, but advanced linear algebra. These tensor operations allow you to start doing things across multiple dimensions like this. So we're seeing, by flipping the order of that, I'm seeing the independence. Of course, you can make it three-dimensional by adding an extra Kronecker on the whole thing. So That's pretty cool as well, and I'm not going to go into that today. So that's the marginal across time. Now, if, as we said, that with the observed process, and I've added the noise in here, is equal to that latent process times x, what we've got is this. So each of those rows of x, our observation y, is equal to this matrix W times the row stack version of x. So this is each of the rows flipped over like that to give us the basis of y before we add the noise, like that. So you can see what I'm driving at now is now I can apply those magical Gaussian rules to find out the new covariance of the system. So it's I chronica W, K chronica I chronica W, plus noise. Because we add noise to everything at the end. Now, there's a nice, easy rule, this is one that's not hard to remember at all, that A chronica B times C chronica D is equal to AC chronica BD. So this tells us that this covariance matrix here is of the form K chronica WW transpose plus I sigma squared. So that's giving us the chronica product is giving us, the WW transpose is giving us the bit of how the correlations are occurring across the outside points. So that is actually the covariance function underlying a simple Kalman filter. If you were to do some various other operations on it, you would start getting other matrices appearing inside here. I think if you, I've not used, because I assume independent processes in the latent space. I don't know what it is called, what the name Kalman gave it to the matrix. If you don't assume independent processes, if you cause them to correlate, from memory, if you cause them to correlate, you get another matrix coming in here, which is representing that correlation. Okay, so that makes it a little bit more general. Do not fit Kalman filters by computing this covariance matrix and inverting it. Okay? Because what you're doing, this is t by t, the length of your time series. This is p by p, which is the number of observations you're watching. And the chronica product between two is TP times TP. Oh, I should have had a joke about Indians there. It just came out. PT times PT, let's say. So PT times PT. So therefore, it's PT cubed. It's a nightmare. PT cubed. You'd never do this, right? In fact, actually, the chronica inverse, you can do this inverse, it turns out, because of this chronica structure, in p cubed, order p cubed plus n cubed. Yeah, so there's ways of doing it already more efficiently, and this thing you can do in q cubed. You still shouldn't do it that way if you've got that conditional independent structure here, because you can do that conditional independent structure, I think, in q squared t, so linear in t, which is why they could do it on a spaceship that was heading towards the moon on a 16-bit computer of the day. If they had tried to invert this, then they wouldn't really have got anywhere. But from a modeling perspective, it shows you what's going on. And the reason I like that thing is because that allows us to introduce something which I think is a very exciting thing about Gaussian processes and also kernel methods. So we wrote this paper, Kernels for Vector Value Functions, a review. This was my student, ex-student, he's an assistant professor now, Maurizio Alvarez and Lorenzo Ravasco, who works in the kernel method side, and myself, we wrote this long paper about covariance structures like this. Because what this is saying is I've got a vector valued function now, right? So I now don't have just time, I also have which different outputs. And I'm telling you the correlations between the output identity and the different times, which is nice. So people use that in things like multitask learning and in all sorts of places. But it's just a sensible way of building a Gaussian process. So this chronica structure that you get is very related to that product of kernels I talked about before. But the difference being here, that the second kernel is a kernel on your output identity. It's not on the original inputs. So that W matrix is like a special kernel, just a matrix actually, WW transpose, which is just indexed back to being a Gaussian covariance, J and J prime. So that's giving us what they call that sometimes is the inter-task transfer, the correlation between the separate tasks. And that form I've written there is actually how you would implement the elements of this covariance matrix. So in fact, it has this chronica structure, but the kernel function now is given by x and x prime, if there's no correlation between j and j prime, this term is 0 and the whole thing is zeroed out. If there's correlation, then this thing's potentially high, and then this x prime exists. So if you've got a function, an output which is uncorrelated with the others, you can consider that. If you've got one that's correlated, you can consider that. So in practice though, if it's just a fixed number of outputs, that's just a matrix. Of course, you can see that you can start doing things like spatiotemporal systems, and people indeed do that. If you've got one thing over space, you could have another thing over time, and then this wouldn't be a matrix, it would be another process. You can combine these things together to build large-scale spatiotemporal systems. So if I just take that matrix WW transpose to be called B, it just has to be positive semi-definite, this matrix, then B is called the co-regionalization matrix. It states how these different output functions are correlated together. So we call this, in our paper, separable covariance functions because they've got this product structure. And this separable structure means there's some ways of doing it efficiently, that order n cubed plus order p cubed that I talked about before. We've still got cubed in there, but we're not cubic in the product of those two things. But you can get really quite complicated. So the things we started playing with Maurizio was sort of forms like this, where you have a sum of these separable structures, with each one having its own separate co-regionalization matrix. So what does this mean? This is just adding kernels in some sense, but it means you can do things like you can sort of say that there's one slow varying process, and that's co-regionalized in one way, and then there's a rapidly varying process that's co-regionalized in a different way. This gets very complex very quickly. In fact, the ironic thing about this is we were trying to build these models as a straw man. We had some very nice work on building these covariance functions with differential equations. Very nice if I do say so myself. And then when we came to it, we said, okay, let's compare with these standard techniques and see how well we do. And these were quite difficult to beat. It turns out that they're very powerful. So we sort of developed our own software for building these things. And you can get these sum of Kronecker things, which is sort of sum of separable kernels. So they're not separable themselves anymore, but they're sum of separable things. So this stuff is known about from geostatistics, where Gaussian processes are called Kriging, or Krigage in French, I think. Krigage? No. These multi-output GPs, so they're pioneered in that, where they're co-Kriging. So Kriging was often about mining, or Kriging, I don't know. About mining. So they're interested in, or geostatistics, so they're interested in, say, how many minerals are in the ground across a different space. And it can be quite difficult. So an example we looked at was heavy metal pollution. So what heavy metal pollution is across a particular region. Now, heavy metals are quite difficult to measure in the soil, they're expensive. But pH is very easy. So you can imagine doing things like you measure a few locations where you measure the heavy metal, and then you measure many locations where you measure the pH. And you build the co-regionalization matrix to tell you the correlation between the pH and the heavy metal. And then you can get a much more detailed map for much less money. Nice, isn't it? That's the sort of thing they do in geostatistics. Okay, so I don't want to overrun, so I just want to sort of show you what these things look like in practice. You, of course, don't have to make this covariance the Kalman filter. I just use that as a way of introducing Gauss-Markov processes and a way of introducing this Kronecker structure. We could just make this a regular Gaussian process that I've done here. And this is just a rank 1. So this is like one latent Gaussian process being mapped out by a W vector, which has two different scales in it. So if I sample from this process, what am I going to see, anyone? It's one latent process that is being scaled to two different outputs. So what are those two outputs going to look like? The obvious thing to see it. They're just scaled versions of each other. Yeah? Very simple. Yeah? Because it's just one latent process being scaled. But if I start making that a full matrix B, this implies, so you see this is why it's nice to sort of know, if you just look at that, you didn't know before that that implies two latent processes, if that's full rank, the matrix B, two latent processes being scaled by two different sets of vectors. So that's a little bit harder to see in the data, right? So there's two latent processes going on here, so they're not exactly correlated to each other anymore. They're doing slightly different things. So, you know, this one goes down here, but this one stays straight. So this is the separable case, and already interesting stuff can happen. The sum of separable case, where you've got two different, that happening twice, over potentially different length scales. So one of the length scales is happening short, and the other one's happening long. So it's co-regionalizing in a different way over the short and long. So it's quite difficult to sort of perceive. In fact, these things get very complicated now. You know, you wouldn't necessarily think that those two things were correlated, would you? But they aren't. Of course, these are joint samples, just to emphasize. You can see actually on this one, there is some correlation here. Just to emphasize what I'm doing here. I'm building that covariance matrix, and then I'm taking one sample. But the first endpoints of that sample are this function, and the second set of endpoints are the other function. And then I'm plotting them separately. Okay. And then there's something called the linear model of co-regionalization. This is quite an interpretable one. So, oh, I lost the equation. Ignore that reference. So this is Yi Tay, Matthias Sager, and I think Mike Jordan, who sort of proposed this form, not knowing about that geostatistics work. So where it's a sum of rank 1 forms. So this is potentially a little bit more interpretable, because now you're saying that each of those latent processes potentially has its own length scale, but then they're seeing some scaled version of those. Because the last one perhaps gets quite hard to interpret. So this is that sort of form. So it's, you know, slightly, the correlations are slightly more obvious than before. And then you sort of get Bonilla et al. Sort of propose this for multitask learning. And there's sort of various things. People doing multi-class classification with this, all sorts of work that has sort of gone around on this. I'm going to leave it there because we're at the 6:15. I did start a little bit late, but rather than torture you further, I will have some questions, I think, and then go on from there. So what have I tried to communicate? I've showed you, I've not really had time. I mean, you should be able to imagine now. I hope that many of you who have your own applications are thinking, oh, that's really cool. I could use that for what I'm doing. Because it's really interpretable and it's really powerful. Of course, it's got limitations. It's got limitations in terms of the size of data you can use, and if your data has discontinuities in it as well. So very often what we end up doing in practice is working on trying to fix those limitations. Taking this very elegant framework and sort of distorting it to try and make it work on real-world data. If you've got real-world data that's coming from the Gaussian process, I mean, this is all absolutely beautiful. But also teach you a little bit about these structured kernels. So that's also useful even if you use support vector machines or whatever to try and understand these kernels from the Gaussian process point of view. And show you that the aspect I didn't tell you about, really, I just mentioned it a few times, is how this relates to signal processing. I think Arthur told you a bit about Bolton's theorem, yeah? Did he, for kernels? Yeah. Yeah, so Bolton's theorem is the way that this relates to signal processing. For positive measures in the Fourier space, they lead to kernels, and you can see them as filters on frequencies in Fourier space. I didn't talk about that, but I showed you how Kalman filters and basis function models are special case Gaussian processes. You don't need to always be doing the Gaussian process inference in the way I showed. Sometimes that's inefficient. But if you don't know how your model relates to these when it does, then, you know, I don't want to say you're ignorant, but you are. And one of the most depressing things for me is that so many people don't know that. And they say such silly things because they don't know that. So even if you're not going to use Gaussian processes, I think having a basic knowledge is key, you know, to how a number of things. You should understand the core facets of them because they're important from a theoretical perspective. Okay, so questions?
So in your co-regionalization framework, and you can use like different length scales for different kernels, is it at all feasible to learn the length scales of each of the individual kernels?
Yeah, it is. Very feasible, actually. So this probably won't work. I should have had these demos ready to go, actually. But we've got a demo, actually, So here's an example where I've sort of played with some data. You can learn the length scales for each of those kernels, but what you're doing is you've introduced a load of parameters in W as well. So you can definitely start overfitting again. So I have an example where it's some data that Mark Girolami and Simon Rogers made available as part of their book, Olympic sprints data, gold medal times over time. I really should have had it as a plot, I keep forgetting to put it in. And the interesting thing is, of course, that in 1896 they didn't allow women to do many sports. So you only get the male times. So what you can do is you can compute the co-regionalization from people moving forward and fit all those parameters and project back. But what I found trying to do that is you can really overfit. So you can really say some stupid, overconfident things about how the female runners would have performed if you're not careful about how you construct these methods, because they're very powerful, they've got a lot of parameters. So the length scales, I'm not quite sure how the length scales interact when they do that, but I think probably the truth is you have to start worrying about sampling again as well. For small data sets, anyway.
Yeah, just one question / comment. So one very small subfamily that I mean, it's part of the Gaussian processes is what people in signal processing like a lot is all this autoregressive process or ARMA.
Yeah, yeah.
And so this, in the sense, it's basically they learn or they are able to generalize by strong assumption that things are stationary across time.
Yeah.
And is there anything that you could tell us to how do you inform? When should you start relying on this assumption or like making your family of, trying to make it closer to this sort of classical families or
For a stationary family.
Yeah, or when do you have enough trust on your data to start going a bit beyond?
Yeah, I think so much of it's domain knowledge. The question was about ARMA models. So in time series prediction and signal processing, people would use ARMA models for system identification. So they're a little bit like the Kalman filter stuff I talked about, but they have little regressions going forward and then a moving average term. So you can show that under Gaussian corruption assumptions that they're also Gaussian processes. Stationarity, I think, is domain dependent. So you can, it depends whether you believe in stationarity or not. So if you're looking for a change point, you're clearly not looking for stationarity. So, I think there's a number of cases where you don't want to use stationarity. But somehow it seems that it's considered a very attractive property for a lot of applications because there's theoretical things you can say about it if it's stationary.
Well, I would say that let's look at practice to predict something, do like extrapolation.
Yeah.
If you don't assume any that the past has no influence on the future, it's very hard to say.
Well, you can assume the past has influence on the future, but for example, the Brownian motion covariance isn't stationary.
Right.
But it's Markov chain. You can get a stationary variant of it by assuming it's occurring in a sort of quadratic shaped field, or linear field, pulling back to the center. Myself, I'm not so worried about stationarity, but I know a lot of people are, so I don't know if it's something wrong with me or other people. I'm guessing it's because you can prove more stuff if it's stationary, and certain covariance functions. So these ones, the Bogner's theorem ones, are all stationary. And linear time invariant system ones are substationary. So there's quite wide classes of stationary covariances which are important. But yes, good point about ARMA, another class of models that can be seen in the Gaussian process. So any other questions? Or you're all raring to do your posters. If not, we'll just end there.